I was kind of over here. The speaker won't see him.
Got it.
He can't see the clock.
Well, it was a bad move.
You know,
Luckily I had my phone timer.
I was learning from that as in real time.
Yeah. Hey, you. Yeah. Over here. Hey. It all worked out in the end.
Yeah, so the secret to the perpetual clock is you never look at the chair holding up the warning sign, how much time we have left. What do you mean? You didn't give me any warning. I got 5 more minutes.
Oh, I'm oblivious. If I miss it, just start throwing.
I tend to do the loom. It's loom over.
Okay,
It works for everyone except Peter Popchin. Who's taller than me. Yeah, loom over him.
Standing up and getting closer and closer.
Yeah, I don't really had to make it super uncomfortable, but I will do that.
I'm-
In the chair.
Somebody has to.
Exactly.
Well, we're gonna do a deep dive. Right.
That's what we like to see.
Mary Ann, can you hear us talking about
Yes,
the
I
deep dive
can.
we're gonna do?
Yes.
We're ready.
Okay.
The audience is ready, just us.
Yeah.
Oh, no.
I'm
My
talking.
bad.
Okay.
Don't worry, I'm gonna go get the audio.
Yeah.
Thank you, John.
I was joking. We're ready in the sense that we're more or less prepared. That was a very.
Yeah. Very-
It's not helping.
As we get later in the day, it's just gonna get worse.
You had enough coffee?
The important thing is Mary Ann should know I am not in charge.
Yeah, yeah.
Dean is in charge. There's a pun here.
Yes, there are many puns here. I will work very
You usually see this.
They announce who the session chairs are beforehand. People will start like citing the session chair. It's like, guys, I'm not giving you 2 more minutes for this.
Oh, it's fun. Yeah, we should go across the people. We have 2 minutes.
I think John went, but,
He did.
okay,
He's too nice.
okay. Thank you. Marianne, I'm not entirely sure how I can give you a heads up on time. I don't know if you have a timer going, but that would be useful.
Okay. We'll try to do that. Get a timer on my end. Feel free to just cut me off if I go too long.
I can just say 5 minutes to 1 minute.
Yeah, that would be good. Really, probably just a 2-minute and I'll be good. I need to rush through the last bit I can.
Yeah, Florida and, they're gonna, one of the 2 of them's gonna figure it out.
Graduates.
Check.
Yeah, some stuff that works there that, 10 years later, there's
Well, I
just
just double
habits
check
in
the
there.
meeting.
So what's
We
inside
went to
here?
the same source.
Put it up.
That means that we made the right decision. It's gonna be really fun to scatter, even more scatterbrained tomorrow.
No, don't want to see that.
Actually, no, yeah.
I need to talk to her about that actually, because there's a couple things I wanted to
But especially the fact that they made their own GPS tabs. I was like, how did they figure that out? I don't know. I didn't-
All right, let's get situated, everyone.
Actually, no. Tonight, I'll go in and I'll bug test. And I'll...
Okay, hi, my name is Deepanand. I'll be chairing the last session of the day, and we'll begin with Mary Ann Limbeck, who will give us a deep dive into the variability and calibration of the JWC Mary imager. Take it away.
All right, thank you. So hi, I'm Mary Ann Limbeck. I'm research faculty here at the University of Michigan, and I'm going to talk to you today about some variability and calibration work we've done with the MIRI imager. Before I get started, I'm sorry I couldn't be there in person, unfortunately. I was planning to, unfortunately. I had a last minute conflict come up and I had to cancel and give this talk virtually, but I'm glad I can still be giving it to you virtually today. Both of these images on this first slide are from MIRI. They're color composites at 7, 18, and 21 microns. Okay, so let's go. All right, so first off, a few key questions that I'll address in this talk. So first, I'm going to talk a little bit about absolute calibration. So typically, the MIRI calibration is done for the imager using main sequence stars at the longer wavelengths. We've had several programs that have looked at white dwarfs at these longer wavelengths, and so it's been interesting to compare how the calibration of those white dwarfs compares to the main sequence stars. And then next, I'm going to talk a bit about how the flat field on MIRI might be drifting over time, and what we're seeing there, and how we think it might be impacting our photometry, and what could possibly be done about it. And then finally, I'm going to end with a brief discussion of the MIRI detector persistence. All right. So as I mentioned, beyond about 15 microns, only main sequence stars are used to calibrate the MIRI imager. So since we just happen to be looking at a lot of white dwarfs at these long waves, it's been a great opportunity to check that the absolute calibration is accurate for those white dwarfs that different calibrators set, comparing to the main sequence stars. So our MIRI, we have several MIRI imaging programs. Most of them collect data at 7, 18, and 21 microns, where we can test to see if these white dwarfs matched the photometry we would expect based on the existing calibration. So these are just a few of those images that we have of nearby white dwarfs. You can see them at the center of the images, all quite faint. One of them has a couple M dwarf companions. And then they all have lots of background sources, background galaxies and stars in the field of view, which really makes for quite lovely images. Okay, so when we're measuring these white dwarfs, what we do is we build a model of the white dwarf based on existing archival visible and near-infrared photometry and spectroscopy. And we use that model to predict the flux we expect out in the mid-infrared. And then we do aperture photometry on our MIRI data to measure the flux of our white dwarfs. And we compare that measured to modeled value. We're specifically interested in the IR excess, so that's what I'm plotting here. And for those white dwarfs that don't have infrared excess, which make great calibrators, you would expect them to land on that 0 line plotted here. So this is the measured compared to modeled value divided by the precision of our measurement. Okay, so you can see that many of the white dwarfs in our sample do line up quite well with that gray line there. They are a little systematically low. So I'll get back to that in a minute. But before I get into all of those great calibrator stars, I do want to mention that we're doing amazing science with these white dwarfs that do have an excess. So we've detected excess in a few systems. This is just one of them where we recently published a paper a couple months ago. This IR excess we see around this white dwarf corresponds to a planet candidate that, if confirmed, is likely about 3 Jupiter masses and 250 Kelvin. A very exciting discovery if it's confirmed, as it's the closest white dwarf exoplanet candidate we found to date. Okay, so back on to the flat lines, which is what we're excited about today. So these systems are the systems with no notable infrared excess. We do see that they are systematically low, but we actually don't think that this has anything to do with the instrument. We think this is more likely our modeling, and specifically, the MIRI imager is at 7 microns calibrated on many white dwarfs, and it's just not at 18 and 21 microns. And so we sort of assume that any offset we see at 7 microns is probably due to our modeling. And in fact, we can anchor our models to the photometry at 7 microns, and that allows us to better understand what's going on at 18 and 21. So we did just that. And when we do that, anchor here at 7 microns, then we do see that here at 18 microns, we're really getting excellent agreement with the existing absolute photometric calibration of the MIRI imager. So you're seeing a nice plus or minus 1 sigma scatter here at 18 microns. Then as we move out to 21 microns, there is still maybe a little bit of a systematic offset to the lower side. This is very low significance, so maybe a 1 sigma offset, but it's sort of questionable whether that's significant or not. What is notable is that out at 21 microns, the signal to noise we get on our white dwarfs is much lower. And so our typical errors are more like plus or minus 5%. And so out here at 21 microns, if there is a 1 sigma offset from the existing calibration, then that would correspond to more like a 5% offset. And so perhaps if we think there's something there, maybe that would be something worth investigating a bit further. But with the existing data, which is relatively low signal to noise, it's hard to say for sure whether or not there is. So I do have several insights of students and postdocs in my group here working on several aspects of this data. So keep an eye out for those as I go through my talk to see who made various plots. And then before I go on, I just wanted to note too that there is, again, a lot of science coming out of these observations we're doing, even though we're focusing on these well-behaved calibrator white dwarfs today. Okay, so we're not sure that, I think the takeaway here is that generally we're finding these white dwarfs are very consistent with the existing absolute photometric calibration of the MIRI imager at these long wavelengths. And that's really great. Maybe there's something going on here at 21 microns. And it's interesting to think about what that could be if there is something going on. And so if there is a discrepancy at 21 microns, what could be causing that? So we all know that there is some structure present in the MIRI imagery. So we correct for this by building a flat from our different dithers and then correcting for that in the image. So this is what it looks like before that correction, and this is after that background subtraction. So when we do that, that works really well. We get these lovely images out that are very uniform in the background. But what's concerning is that when we do photometry before and after our background subtraction, we do get slightly discrepant values. So we're looking at changes in our photometric values of about 3 to 5% from before versus after subtraction. And what's concerning about this is we're not sure which measurement is accurate. So we have been talking to some folks at Space Telescope about this and discussing different ways which we can do the subtraction. And so we plan to try to do that a few different ways and see if that changes the photometry that we're getting out in a way that would make it more consistent between the before and after subtraction methods, and see if that resolves the issue by itself or if we need to look into this further. But regardless of what happens there, we have found that this background structure that we're seeing does seem to be increasing over time. So specifically, I think back to, well, so we all know that MIRI experienced this reduced count rate early on in this lifetime. So this is a well-known thing. And here, we think that perhaps if this reduced count rate was caused by a decrease in transmission from one of the optical elements inside the MIRI instrument, it would seem reasonable that we might also expect an increase in emission from that same element that would correspond to some change in the flat field. And so this is an interesting idea that we thought perhaps worth testing. And so we set out to do this. And our goal here, so there can also be an increase in the background just from depending on where we're pointed in the sky. And we really want to separate out things that are internal to the instrument versus things that are from the sky background. And so when we're constructing these flats, which look like this, we basically take observations from several different targets over a small interval of time and construct these flat fields. And then what we do is we look at the ratio of this dark region, which we see compared to this light region. And by tracking the amplitude of that ratio, we can understand what's going on in terms of the flat. So we think that's due to some internal change in the instrument rather than what's due to the sky background, which is more likely to be an overall amplitude change. Okay, so we've been tracking this ratio of the dark region to the light region. And when we do that, this is what we get. So we see right around the launch of JWST, there was no amplitude difference. So that was a uniform flat field. And then as time has gone on, that amplitude has increased. And specifically, we see an amplitude of about 1% right now. So you might be thinking that an amplitude of 1% isn't that much, but the issue is at 21 microns, often our white dwarfs are also about 1% the flux of the background. And so when we have this amplitude variation, that's comparable in flux to the amount of flux we get from our science source, it's quite reasonable that this feature in the flat field might be impacting our white dwarf photometry. So there's a couple other interesting things about this. The first is this seems to be getting sort of linearly increasing in time, which is not what we saw with the MIRI reduced rate count change. And so perhaps this isn't exactly the same as what was going on there and correlated with the same optics. It is a bit alarming that it doesn't seem to be tapering off. Certainly if it continues to increase, it's quite possible that it will impact things beyond what we're seeing already. And I think something that's worth looking into more. So I think if we want to understand better what's going on here, it would be useful to perhaps consider including faint stars as MIRI calibrators. Those faint stars are going to be much more impacted by these non-uniformities in the flat field. And so it'll be easier to ensure that we're understanding how that is changing over time and ensure that we're accounting for that in the pipeline and data analysis process. So that's the key takeaway there. And then the last thing we did with our data was this unintentional measurement of detector persistence. So it just turned out that one of the white dwarf systems that we observed happened to have a very bright M dwarf companion. And this companion saturated the detector. So this imaging sequence was at 7, 18, and 21 microns. So the 7 micron data saturated the worst, and then we imaged in the other bands. And when that happened, this is what we got. So this top panel here is showing the 21 micron data shortly after that 7 micron saturation had occurred. So you can see at 7 microns, the clear dither pattern left behind in the stage 2 data from where that star had saturated before. So this is about 12 minutes after saturation. And then about an hour later, we went and looked at a different white dwarf system. And here you can see that dither pattern is still present on the detector. So it's particularly easy to see this at 21 microns because the sky background is really high. And so even though the detector persistence is only about 1%, 1% of a very high sky background is still enough to be easily detectable on the detector. Okay, so what we did was we took this and tried to see how fast the detector persistence was falling off. To make that measurement, we basically looked at the flux deficit in this dithered region compared to the sky background. And when we did that, we got this. So we found a flux deficit of about 1.5% immediately after that saturation. Okay, and then it was down to about 1% after just about an hour. And based on this, we're predicting that it would fall off to less than 0.1% after about 6 hours. So of course we do only have 2 data points here, but it does look like there are a lot of other data sets in the archive where you could add on to this and perhaps get a good understanding of how much scatter there is about this decay time. But that was a fun measurement nonetheless. Okay, so I think that's it. I'll end there and leave up my conclusions and take any questions.
All right, questions. I don't know if the room mics are working. I'll just hand the mic around.
I just have a real simple question because I don't know much about the Miri detector, but why do you only get 2 points? Isn't it always giving data all the time?
Yeah,
So why are they like?
To make this measurement of the detector persistence, basically what we're doing is, this is 12 minutes after the saturation occurred. We read out, the detector at these 4 dithers. And basically we make a measurement in these 4 dithers of the deficit, the flux deficit. And then based on the scatter, we sort of get the error bars on our measurement between the 4. And so it's just that we only looked at these 2 stars, like only this data was saved from the detector. So this is the only data that we can access with the dither pattern still on it. Yeah.
So looking at this image, is the latent also in the slew between dithers? Is that what we're seeing? Yeah.
Yes,
okay.
that's right. Because there is no shutter, right? So it's always exposed to the sky, and so the saturation is getting dragged. The star is getting dragged across the detector as it's moving to different positions.
Right, but now does Miri? Somebody should know whether or not Miri's operating where they reset. You reset between integrations, right? Yeah.
Yes. So when we're not integrating up the ramp, right, then we reset every frame.
So,
but this is a really bright star.
So the reset is what, 3 seconds? Or?
Yes. I mean, I was going to say, Marianne, this is Carl Gordon. Awesome talk. Neat to see. Nice to see the white dwarfs are at least close in the long wavelengths, if not pretty good. I've seen this pattern before. And it happens when we have a very bright source. So it's very neat to see you've measured the time constant. Yes, we have persistence. I'm waiting for someone in the world to come up with a model that might work.
Questions online or?
I'm online.
I'm assuming there was at least one help desk ticket from all this.
Yeah, that's definitely true.
Perfect. This is a cycling pattern, right?
Yeah, that's right. 1 to 4.
Yeah, I'm just thinking that what we should be doing is we should recommend that people using cycling pattern and different observations in their program should start at different points so they get different patterns. But
I don't think you can do that in one visit.
Yeah.
Don't do really bright targets.
It was really quite sad. Yeah, in this image, this is actually the white dwarf, and at one of the dithers, it very sadly lands right behind this dither pattern. Fortunately, in the other 3, it's fine, but yeah, on both white dwarfs, it lands behind the persistence in one of the exposures.
At least it was your own data doing it to you, not someone else's data, which also happens.
That's true.
All right, let's give Marianne another round of applause.
because it's integrating.
We just have to share. Don't know how that works.
Sure they are.
Oh, we have to recover from being in the unusual configuration.
Yeah, so do I just share from up here?
That's really bright source to get that. Surprisingly, I've seen.
Hoping Kevin is on his way.
You're gonna see it on all these cameras. How did that work?
Oh,
Dope, so we got.
Seems to be online too, so.
Perfect. Whatever y'all did, thanks.
Survive power.
Oh, that's the usual.
Yeah.
There's no F keys on this student.
Yeah, I don't.
We can see that.
Do we know how to full screen on preview?
View?
View,
Oh, last one.
either slideshow or enter full screen. I don't know which.
Take that.
All right. Next up, Jamie Terror will be telling us about current flux calibrations and how they limit stellar age estimates.
Right. So this is a talk that's responsive to the question that somebody asked on Tuesday, which is why are we doing this flux calibration? Right? You guys are all working very, very hard to do this very precisely. And what are the science cases that it impacts? And so I'm going to talk to you today about how this impacts our understanding of stellar ages. And I like talking about stellar ages because they cut across a wide range of communities. For people who are doing exoplanets, sometimes they want to know how their planets are evolving with age. For people who are studying kind of stars in the Milky Way galaxy, you're looking to understand the age evolution of our own, our own local area. And even people who are doing kind of extragalactic work are trying to understand the stellar populations in those galaxies, how they've evolved over time, how those galaxies formed, when those galaxies formed, and how that relates to our understanding of the physics of the universe at that time. And so most of those things would be really nice if you could tag with an age what is happening. So how do we get ages for stars? In reality, there's kind of two things you need to do to estimate a stellar ages. One, you take known stellar parameters. The kind of default choice is to take, say, a temperature, a luminosity, and a metallicity of a star. But you can take kind of any known stellar parameters. And then the second thing you need to do is you need to look up in some grid of stellar evolution models how old a star with those properties is. So for the first half of that, there are uncertainties on those stellar properties. Now, people in this room who are studying individual stars very carefully perhaps have smaller error bars than average. But for the majority of the stars in the sky at this point, we're talking about luminosity uncertainties of about 2 or 2.5% that come from things like photometric zero points, offsets between surveys, atmospheric models, redditing maps, spots on the stars, and so on. And similarly, there are temperature uncertainties of roughly 2% for kind of your average star in the sky, which come from those luminosity uncertainties, the effects of our uncertainties in angular diameters, and so on. If you're using something like a metallicity, there are all sorts of systematics in that. We're not going to unpack that today at all. And then, it's possible that you maybe have more than 3 parameters, and maybe you can use that extra information in some way to improve your inference and reduce your uncertainties. But in kind of the simplest case, you're looking at a star. It has some temperature and some luminosity, and I've added that little kind of pinkish magenta cross to kind of give you a sense of what those uncertainties look like on a plot like this. And then the large dashed line gives you the location of where stars of about 1 gigayear in age are located. And the solid line gives you a sense of where stars of about 5 gigayears in age are located. So, if you're looking at stars kind of on the subgiant branch, so kind of in that region between the main sequence and the red giant branch, there's a pretty big difference between a 1 gigayear star and a 5 gigayear star. So at that point, your observational uncertainties are not a huge contributor to what's going on here, and you can probably get a very precise age. That's kind of the color coding of the points here. But if you're looking at a star that's kind of closer to the main sequence, maybe it's a lower mass star, so it's kind of down on this track, you can start to see those 5 gigayear and 1 gigayear lines start to get closer together. And if you kind of compare by eye to those uncertainties in the measurements, you can see where those would start to become a little more important. And similarly, if you're working on red giant stars, maybe you're trying to do work with more distant stars, again, the models are kind of collapsing together to a place where the 1 gigayear-old track and the 5 gigayear-old track are not that different. And so uncertainties in the measurements can contribute to your uncertainty in the age at a significant level. Okay, so that's part one. Part two is you have to look up the answer in a grid of stellar models, right? I showed you some, demonstrative example, but in reality, somebody is making a model of the evolution of a star. They're assuming things probably like spherical symmetry. They're assuming things like conservation of mass, conservation of energy, hydrostatic equilibrium. And basically you're saying, okay, I'm going to burn fuel in my center. That will change my temperatures. So I will update the stellar structure, which will cause me to burn fuel. And you basically take a time step and a time step and a time step, evolving the properties of that star over time. And so you can map out its motion through the HR diagram. And so you take an input, you say, okay, I want to model a star of 1 solar mass. I want to model a star of solar composition. I'm going to assume that it's not rotating at all. That makes things too annoying. And then I plug it into my modeling code. That modeling code has some physical assumptions, like conservation of energy, and it's set up to solve a set of coupled differential equations and produce one of these stellar evolution models. So you can watch the star evolve from the main sequence to the subgiant branch, up the red giant branch, and so on. And so you can do this for stars at a variety of masses, 0.6, 0.7, 0.8, 0.9, 1.0, make these different tracks and say, okay, now I have a sense of where a star of a particular mass or a particular age should be on this diagram. And if I observe some stars, I've just picked a couple, they line up in this diagram, and the star that is between the 1 solar mass line and the 1.1 solar mass line is probably 1.04 solar masses. Sure. But when I showed you this slide of how the models are working, I had a line that says has physics assumptions. And that's a little concerning, because what that means is if you go to one person's model grid, looks like this, right? You have some numbers, you get some numbers with some uncertainties from the stellar mass and the stellar age. And if you use a slightly different model grid, those lines are in a slightly different place. So I can kind of flip back and forth, and you can see that, topologically, they're in a similar place, but they're not in the exact same place. And that means that what model you use is going to change what you infer for the mass and the age. And if you're thinking about, what that difference is in age is, we can map that out by comparing the results from different models. And so what I've done here is say, for several different model grids that people are using, they're all generated under, using their best assumptions that they can about the physics of the stars. You can map out where they're the same and where they are different. The color scale on this plot goes from 0 to 50% differences in age, which is a problem if you're trying to infer something about the evolution of the universe. Now, there are regions where we're doing okay. That bit in the middle where we were talking about, the models are very far apart between 1 gigayear and 5 gigayears, you have a relatively limited model dependence, and so you can get a pretty good age. But if you're close to the 0 age main sequence, changing the location of that 0 age main sequence takes you from being 0 years old to being a gigayear old, and that is 100% change in your age. And so, you see kind of that dark blue line along the 0 age main sequence because we don't exactly agree where that should be located. And then for this paper, I said the giants are bad. And I topped off the color scale at 50% because I didn't even want to deal with that. Luckily, I now have a very talented graduate student, Leslie Morales, who's been looking at the giants specifically. And so she's gone through, she's expanded the color scale. It now goes up to a 90% difference in age if you look them up as a function of temperature, luminosity, and metallicity. And so what she's been finding is that the models agree better kind of in these less evolved stars, kind of end of the subgiant branch, kind of making that turn up the giant branch. You have a 10, 20, maybe 30% uncertainty in your age, but you can do this. But if you're looking up something that is actually a giant at a luminosity of 100 or 1,000 solar luminosities, the models disagree significantly on where a 5 gigayear-old star should live. And so if you're trying to infer an age, you will get a very different answer depending on which model grid you ask. And she's also mapped out kind of a sense of where does the observational uncertainty, dominate the error budget versus where does the theoretical uncertainty dominate the error budget. So for these most evolved giants, the coolest giants, the theoretical uncertainty is the biggest problem. There's a 90% uncertainty your observational uncertainties don't matter. But as you get to a regime where the models agree better, suddenly your observational errors start to dominate. And so that's kind of those subgiants and lower giants in the blue side there. And so that means when we want to get better ages, we have to think in kind of two different regimes, because nobody wants an age error bar of 100%. We'd love to do better than that. So in regions where the observational uncertainties dominate, then we start asking, can we get better observations? Can you get us better temperatures? Can you get us better luminosities? Can you get us better absolute fluxes? And that pretty directly translates what's been happening here at this meeting to better ages for stars. But then on the other end, where the theoretical error dominates, right now we're getting that theoretical error by saying what is the difference between any two grids of models, assuming that all grids are equally good. But presumably, not all grids are equally good in each regime for each type of star. Presumably, there's a right answer. The stars know what age and mass and temperature they are. So can we figure out which one is right and use that one? And so you can take, systems that we've characterized very well. This is an eclipsing binary, so we have a mass, we have a radius, we have a luminosity, we have a temperature, disentangle the two stars, put those 2 points, those 2 black points with very small error bars on a plot like this, and run 4 different models and say which one matches the properties of both stars at the same age. And the answer is none of them. So in terms of what model is right, the answer is probably none of them are right. And so, that's not great. And so what we're hoping to do, and the reason that I got involved in things like the Landolt mission, is we're trying to find more stars where we can figure out what the right answer is. What is the actual absolute flux, absolute temperature, absolute luminosity, so that I can compare directly to these models in the regime where the models are actually predicting things. And can I provide a set of calibration stars with known parameters where we can start to anchor these models and figure out, what are the right answers? So what we're trying to do is kind of push on this in a couple of different directions. Can we get more calibration systems? Things like clusters or eclipsing binaries or stars with very well measured properties, can we check whether the models get them right? We also want to work on the model side. What are these physical assumptions that are going into the models that are changing one model grid from another? How do they map to changes on the HR diagram? And then can we combine the two to produce a grid of calibrated models that anyone who wants to get an age can use? And maybe not everything is perfect about them, but at least they're kind of giving you the right answer in the regime that you care about. And so hopefully I've convinced you that ages are one of these derived quantities that inherit all of the observational and theoretical uncertainties from upstream. And that things like the FLUX calibration can limit our stellar age estimates at this time. And so, we have direct issues where we don't know the properties of the star well enough to infer the ages to better precision. And we also have regimes where we don't know the models well enough to choose which one we should be using to infer the age. So we're hoping that upcoming work on things like Landolt will help us better these properties of calibration stars. Thank you, and I'll take any questions.
Thanks for the great talk, Jamie. Questions?
So there's a lot of well-studied eclipsing binaries with normally really, really accurate parameters. Wouldn't that be the first thing you'd go to?
Yeah, so the eclipsing binaries are definitely going to be one of our major calibrators. There are some things where different eclipsing binaries are processed in slightly different ways by slightly different people. And so if you use something like the detached eclipsing binary catalog and just kind of pull the data from the catalog, it's not actually homogeneous enough to like force you to get the same answer in all places. But as we've got these bigger surveys where people are doing the spectroscopy, they're using similar tools like Phoebe, and they're starting to use like eclipses from tests where everybody's kind of running the same procedure, we're starting to shake out a set of stars with not only really good relative parameters, but really good absolute parameters. And I think they're going to make a huge difference in how we do ages.
Hi, John Debus. People have had some success finding ages through rotation rates and astroseismology. So are you also considering those populations as calibrators?
Yes, so people use a variety of other techniques to estimate ages, but all of those are actually calibrated back to this technique. Because when you think about the rotation ages, you're basically using some gyrochronology where you say a cluster is this age, and the stars of this color at this age have this rotation period. And therefore, if I have a rotation period for some random star of that same color, I can interpolate it's between cluster A and cluster B. But that means that somebody fit the age of the cluster using one of these models at some point. And actually, if you look at like M67, the uncertainty on that age is 10%. And so that folds through to all of those calculations. So yes, I would love to use them, but I think they have to be secondary calibrators rather than the primary things we calibrate to.
That's good with the microphone.
Oh, just here.
Do you know the metallicity of that eclipse binary? That
AI phi is pretty close to solar, I think. I don't remember if it's minus 0.2 or plus 0.2, but it's something in that range. It's pretty close.
okay, so it's known because
It is known. It is known.
David and Arnett pointed out to me that the vast majority of the eclipsing binaries, even though have 1 to 2% errors in masses and radii, they don't have measurements of metallicity and
Yes.
they are assumed to be solar.
Yes, that historically has been a big problem for several of the systems. It still is, because disentangling the spectrum, they pick up an uncertainty term, which propagates into their metallicity term. Some of them, the brightnesses or the colors are different enough. Like this one has a pretty good span difference in temperature, which gives you a slightly better chance of getting an actual metallicity from the disentangling. But one has to be very careful on those sorts of things, for sure.
Anything online? Any more questions? Oh, one in the back.
You mentioned that you're using models that people use, but I wanted to just ask out of curiosity, which models did you actually incorporate and how did you make sure that those models were ones that are used?
Right, so for these, the plots I showed you today incorporate models from the Yale Rotating Evolution Code, MIST from the MESA code, DCEP from the Dartmouth code, and the GARSTEC models from Aldo Serenelli. So that's it's not everything that everyone has ever used, right? Parsec is another one that's very common, but it kind of gives you a span of things that were calibrated in weird ways for specific problems versus things that are used across the HR diagram, things that are used for more low mass stars and more high mass stars, kind of giving people a sense of what's out there. Yeah.
And we do have one online question from Everett Schlane. Similar to a previous question, with better flux calibration and information about the stellar density from transits, can planet host stars be better constrained with luminosity than other techniques like gyrochronology?
Yes. That is, I think, where we're going to end up. So you've set up Dan Stevens' talk, which is coming right next, in a beautiful way, because I think that might be the right answer. That you use a sense where you have some other physical estimate from the orbit of some parameter, which now you have enough independent things where you can start to cross-calibrate. And you don't want to have to deal with the spectral disentangling in an ugly way. So it's nice if it's something like a planet that doesn't really have its own spectrum in most of the bands that we're looking at. So I'm going to pass you right over to Dan on that question.
All right, with that, let's give Jamie another round of applause. And now Dan Stevens will talk about how single-lined eclipsing binaries can become better benchmark binaries with better flux calibrations.
All right, can everyone hear me okay? All right, so I'm Dan Stevens. I'm a Nintendo astronomer. Here to tell you about a problem I have and how all of you are going to help me fix it, whether you want to or not. So thank you for your cooperation over the next several years. Right, so one may think that eclipsing binaries are a solved problem. We've got a couple hundred at this point. I think over 300, where we've got masses and radii measured to 2% precision and accuracy. So, you know, with ideal cases, we can measure individual masses, individual radii, individual temperatures of the two stars in the system. And we've done this a lot. I'm going to focus my talk mostly on the challenge of doing this for low mass main sequence stars, so like 2 M dwarfs in an eclipsing binary. But a lot of what I say can be generalized to other systems as well. But for these specifically, you know, these eclipsing binaries are dim. They limit your signal to noise. For shorter period systems, they tend to be pretty active. So you've got flares, you've got flux modulation due to star spots, complex spectra, right? M-dwarf spectra are complicated. Now you have another M-dwarf spectrum on top of that first spectrum. You're having a great time already. And so if you look at the detached EB catalog, which has, again, exquisite masses and radii for most of the stars in it, there aren't a ton of low mass main sequence stars. So there are a few dozen at this point. And even among those few dozen, not all of them have metallicities. I think Fe upon H is still pretty hard to come by in that catalog, just illustrating some of the challenges that we still have, even though we've known how to get stellar parameters out of these things for more than a century. So I propose instead to remove the spectrum of one of the two stars and see how far we can go. Single line EBs, in contrast to their double line EB counterparts, well, if we are focusing on those dim M dwarfs, we've now paired them up with a more luminous star that is, in theory, better behaved. It's easier to measure the metallicity because you've got one spectrum of a more luminous, better behaved star that's not covered in molecular lines. Great. Components can also span the HR diagram. So this is actually probably not even the third best example I could have pulled, but even so, thank you, Jamie, for making this plot, of a case where we have a low mass star all the way in the bottom right, and a more evolved star just coming off the main sequence up in the upper left. And so we can really span the HR diagram, test our stellar models across this wide dynamic range. And you may notice that there's a third cross on here. So I've got my primary star, my secondary star, and because this is an analysis that uses test data and we've got 21 arcsecond pixels, you have to do a little due diligence, get some high resolution imaging, and of course there's an interloper in the system. Not yet sure if it's gravitationally bound, but it is there. So this is speckle imaging, where you see the EB in the center and then the duplicated image of a third luminous thing in the test aperture. So the analyses may be less complicated. The closer you look, of course, the more complicated it gets. But you can use, in principle, similar tools that you use to analyze transiting exoplanet systems for an FM eclipsing binary. And so if you'll bear with me for a toy model here, piecewise linear transit model, we've got the depth of the transit delta, the duration, or the full width half max duration, the in or egress duration, so we're assuming a circular orbit, and an orbital period. We can get relative radii, just from the depth, assuming an edge on orbit. Radius of the primary star scaled to the size of the orbit. And a combination of density terms where, if the second object is much smaller than the first, you pretty much get the density of the primary object. And so this is the technique that Jamie was alluding to, of getting a transit density for a host star. The problem is that if you look at the spectrum, you only see one, and so you can only measure the radial velocity variation of the more luminous thing. So you don't get a nice clean mass ratio in sum of masses, you get a mass function. We can break this degeneracy now by turning to the spectral energy distribution. So if you have an effective temperature from the spectrum or the SED itself, an exquisite distance from Gaia, and a bolometric flux by observing the star at multiple wavelengths, fit a stellar atmosphere to it. Here you're seeing the green spectrum of an M dwarf and an FM binary. The red, which you can't see because it's directly behind the black, it's for the primary star, and the black is the composite model atmosphere. So we can get radii, at least for the more luminous thing, from this. But one of the challenges is that that radius is pretty sensitive to uncertainties on temperature and bolometric flux. Right? So it's also true for the companion because the radius ratio is what we get from the transit. And so we can get R2 if we know R1. The error on R2 goes as the error on R1, which goes as roughly half the uncertainty on the bolometric flux, roughly twice the uncertainty on the effective temperature. We're ignoring covariances in this analysis. And so we're pretty sensitive to how well we know the effective temperature of the primary star. The mass errors are set by the uncertainties on the primary stellar radius, which are set by those uncertainties on the effective temperature. And sometimes also by the uncertainty on the transit density. Because remember, mass goes as density times radius cubed. But we can measure densities and also depths from transits to 1% or better pretty routinely. If you pull up the Exoplanet archive right now and you were just to flip through and look at the fractional uncertainty on RP over R star and the density of the star, you'll find that over 1,000 of those systems have sub% precision quoted. So largely, our error budgets are being dominated by the errors on the SED parameters, and specifically temperature and bolometric flux. Now, the situation is a little bit better if we're looking at the mass of the companion, because it goes as the total mass to the 2/3 from the mass function I showed earlier. So if you want to get a more precise measurement of your M dwarf's mass or your planet's mass, assuming you can measure their RV semi-amplitude to high precision, you don't need, you can do a little bit better than you can do for the primary. All right, so how bad is this? Let's assume you care about M dwarf radius inflation, and you want to know why the models predict radii for M dwarfs that are 5 to 15% too small compared to what we observe, and why the temperatures are about a few percent too hot. Now, this is a statement made for mostly M dwarfs and double line EBs. You might want to investigate whether or not the single line EB M dwarfs show the same features. And maybe if it's a function of binary star interactions, you might want to look at M dwarfs in EBs at very long periods, which, looking at this plot, we don't really have a ton of. A lot of the M dwarfs in double line EBs with 2% mass and radius measurements are on orbital periods of a day, a couple days, or less than a day, where you might expect strong tidal interactions to produce a star that does not look like your single star model looks like. So here's an 18-day orbital period, FMEB. We've got multiple primary and secondary eclipses from TESS. We don't see anything else astrophysically interesting in the light curve. We've got a great radial velocity orbit from the trace spectrograph, not shown here. And we've got broadband photometry from Tycho 2, 2MASS, and WISE. We also have a Gaia DR3 parallax that is so exquisite that I didn't even make a note of the fractional precision on it because it does not really factor into the error budget. This analysis uses a lightly modified version of ExoFast V2 capable of fitting an arbitrary number of stellar SEDs using filter profiles from the SVO's filter profile service, where it's been lightly modified to compute the secondary eclipse depths and the luminosity ratios from the SEDs themselves. So right now, the achievable precision that we can get, about a little less than 1% on effective temperatures, 3% on bolometric fluxes, which means we can get percent level radii and few percent masses. Not bad, but 3% on mass, we need to do better if we're looking for few percent level effects, few percent differences from model predictions. So can we take these single line EBs and make them detached EB catalog caliber? Can we get to 2% or better precision? And the answer is yes, if we could add spectrophotometry from Gaia, shown here, impossible to see in the blue curve. Add that to our SED fit. And now our precision goes down to 0.5% in temperature, about 1% in bolometric flux. And we can get at least the M dwarf's mass to 2% now. Great. We can still do better. And so for the cases where we have a Gaia spectrum and an optimistic case where we've got like the right brightness such that we have a very good FLUX spectrum as well without saturating, we showed in 2018 that we could expect to get sub% radii from SEDs for FGK type dwarfs. And we measure, if we combine this with broadband photometry, anywhere between 90% of the flux, as is the case for this A5 dwarf, all the way to 98% of the flux for FGK and even some M's. And now we get precisions that are, frankly, exquisite. Double line EB catalog ready. As you all know, precision is not accuracy. So we've got some systematic error floors that Jamie has done a good job quantifying with collaborators, which sort of ruins this talk and makes the uncertainties, if you actually account for this, quite large, like unwieldy. So this method does not really work if you account for this, which is why we need your help. We're able to achieve sub% absolute flux calibration. We're able to reduce systematic error floors in temperature below 1%. Suddenly, we're able to get errors on single line EB parameters that are limited once again by the precision and the wavelength coverage of our data. And so we could start poking at these same fundamental physics problems that we've been poking at with the double line EBs, but now with a much larger sample of stars. So I have a spreadsheet, just myself and the Kelp follow-up network of 200 of these things, right? And waiting for just the data, the systematic error floors to be reduced, and more people than just me to analyze them. So we really want to leverage and fully exploit what the next few years are going to bring in terms of the precision of the data. We need to start lowering these floors. And this is where I'll end with just an advertisement for our master's program at the University of Minnesota Duluth. If you have questions about it, please ask me. Thank you.
Thanks for the talk, Daniel. Questions? In the back.
Is there a constraint? I would think there would be a constraint from if the radius, at some point the detached binary becomes an attached binary, and starts looking very different. So there should be like a tip of the radius distribution that corresponds to that point. Can that give a independent, any precision there?
Could you repeat the beginning part of that?
So, at some point, for the very close in detached binaries, as the with the large radius of the stars, at some point it becomes an attached binary, and so does that point, that tip of the radius distribution give a calibration point?
Ooh. So off the top of my head, I'm not immediately sure. I know, there's a lot of effort done to tile the surfaces of stars with geometric shapes and account for deformity as you start approaching the border between detached and semi-detached. I also know that there's been a lot of effort towards finding analytical prescriptions that describe how the brightnesses of binaries change as a function of tidal distortions. I also know that there are a few prescriptions out there. I also know they're all mostly assuming an equilibrium tide theory, and they don't necessarily produce physical parameters that agree with what you get from eclipse and RV modeling, and not necessarily in a systematic way. So in theory, there's probably something you can do there. In practice, I think it's tricky and requires having a large set of homogeneously analyzed detached EBs that you could use as a point of comparison with your homogeneously analyzed, maybe semi-detached EBs. Happy to talk offline if I only quasi answered that question, which I think I did, at best.
Any more?
Would you like to comment on those red points on there as preliminary?
Yeah, notice I put a preliminary in italics to emphasize the fact that maybe you shouldn't trust those yet, but just to illustrate what we could do in the period range we can get out to. But generally, I am seeing that the MDORs in these systems have somewhat cooler temperatures than models predict. I don't know if I would commit to 20% right now. I probably wouldn't bet anything on it, but 10%, sure. Why? Great question. And I'd love to get an answer because the folks I've asked don't really know.
But now you made it angry.
Yeah, sorry. Finish your talk early enough that I forgot about it.
That's rare. I never do that.
Any more questions?
Anything else?
Oh,
So there's also M dwarfs around white dwarfs, and some of them eclipse. Is that a viable population to supplement what you're doing here? Less or different model uncertainties?
Yeah, so I think that's a good question, and I'm not as intimately familiar with those, but I know wet dwarf, M dwarf binaries have been used to probe the M dwarf radius inflation problem that way. So I presume yes, though if there's someone in the room or on Zoom who can correct me, that would be a great time to jump in and tell me I'm wrong. But again, I think maybe the trick is making sure they're homogeneously analyzed too.
So I have a naive question. Luminosities are normalized to solar luminosity in a lot of the vertical axes that you put up. Does that mean that it would be sufficient to measure these luminosities relative to the sun, or is there implicitly an absolute bolometric energy output here that is sort of hidden in that normalization? You understand my confusion?
So I'm not sure because I don't know that I'm making any claim about normalizing the solar luminosity. So what I should have said is that the statement about M dwarf radius inflation that I'm making and these plots that I'm showing are at fixed mass. So I'm matching the mass. I'm matching the mass that I measure to the mass of a model. And I know that, you see radius inflation, temperature suppression. If you do r squared t to the fourth, you will in some but not all cases match the luminosity of the model. So no, I'm not quite sure.
There's no more questions, then we can give Dale another round of applause. There's a session. I don't know what the session is, so.
Discussion session.
There's a discussion. Yeah.
Discussion, yes.
All right, we're going to talk about ground-based to space calibration. And I'm not going to talk at all. I'm going to just.
I'm reactable.
Okay. Yeah. And so let's try. So, I mean, we heard a lot about trying to reach maybe below 1% accuracy in the spectrometry, right? Now, when I started my career as a student, I was surrounded by a number of people doing accurate photometry using old-style photometers, the Geneva Strogan photometry. And there is this recent catalog, 2022, and they went back to all the Geneva photometry, and they include 42,911 entries of high accuracy photometry. So what did they mean there? They have the absolute photometry to better than 1 magnitude and 80% even better than 5 millimagnitude. And the color was accurate to of the order of a few percent. I don't find the number. So this has been achieved from the ground. Of course, they spent a lot of time doing that. I mean, doing this old-style photometry is, time consuming. I mean, they were looking at the sky. Is there any cybers there? If not, it's not worth observing. But basically, in a way, aren't we trying to reproduce this on very large amount of stars on CCDs, on CMOS, and then try to see how we match the space-based observations. So what prevents us to do something like that? Or do we go from ground-based to space-based or opposite? So these are some questions that I have. You probably have a lot of other ones, but okay, let's start.
So yeah, I think you're right. Actually, in the 1970s, people who did photomultiplier photoelectric photometry were getting to millimagnitude precisions, and then CCDs happened, and it set everything back by 2 orders of magnitude. in terms of because the original CCDs were really terrible, right? And so actually, we've been slowly working our way up. And if you go back and read papers, in particular by Young, I would advise we're just basically catching up to that precision frontier that silicon imagers set us back from, actually.
Yes, I was actually at Los Campanas once with Arlo, and he started using CCDs and was very disappointed. But we emulated what he did, right? Photomultipliers used to re-image the pupil of the telescope onto a photodiode. So the star moves around, it doesn't move the pupil around. So with Eric Gaidos and his grad student, we did defocus and just stuck the stars on the exact same pixels every time, and we got millimag on Mauna Kea open loop. Go to this star, that star, that star, that star. Not the same field of view, not the same time. Just go around like they used to do in the old days. So it's not understanding how to get the data of the CCDs correctly.
Now, the Geneva have now 1 meter telescope atlas. They use CCD, so they also reach this kind of accuracy.
It's not, is it relative or open loop? Lots of people will say, I got that, but I had 20 stars in my field, and I photometered this one, and it's relative. That's not what I'm talking about. Well, completely open loop. I'm looking at one star at a time.
So, Rick, in your introductory thought, you were talking about, something that worries me since that we were doing flat fields wrong. Because what we are doing with flat fields, we are basically trying to try something. We are trying to try basically the individual response curve of the pixels, but it's actually not what we are supposed to do.
Yeah, that's what Chris was showing. And for our experiment, we tried flat fielding because it's what everyone does and that ruined everything. We just stayed on the same pixels all the time, millimag.
Did you then observe your standard stars on the same pixels? Is that how you got the photometry from precision to accuracy?
Yeah, we would go and acquire it, and they were bright M stars because these were exoplanet guys, and they were frustrated. They wanted to find, look at bright M star potential exoplanet hosts. Well, there aren't field stars where you can get a 5th magnitude M star and a bunch of field stars, do relative photometry, and look for transits. So they wanted to see, could they do this open loop? So that was the experiment. It was like one night. But so we'd focus, figure out where it was, defocus, take the exposure, move on to the next one.
And I think another point which is important is, also doing the same thing that you were saying is we are observing the object and the calibrator in the same way on the same pixels. Yeah, Abhi.
There's a possible problem that stars that were being observed then to millimag accuracy, are they too bright for today's space experiments?
It's likely the case because they have been obtained with relatively small telescopes, I'd say 50 centimeter telescope, 1 meter at most. But in a way, I think that we should be able, when we do, people have been searching for variability on using Hawkeye, one of the instruments at panel using Hawkeye. And there they were basically defocusing, so trying to spread the light on many more pixels in order to try to have as many photons as possible.
But defocusing also changes the optical train.
Yes. No, it's not a solution to everything. Yeah.
So when you say absolute flux calibration, I imagine two things. And again, I'm a newbie, so take me at my word. One, traceable to the SI system. Two, all the uncertainties are chained and traceable. I think that even in the early examples that you give, that was not the case. It might have been SI traceable, definitely the change of errors not. And from what I could see in the tables, all of them are above 1% or around 1%. So I'm not sure, if what's the state of the art, but you can tell me. You're the
Well, I would have to look back into all this and what actually they mean there. But it's, it's always something curious to me. But the thing is that they were spending much more time on calibration of the atmosphere, trying to get the extension right. At Parana now, we came back to this. We basically assumed that the extension is all the same. But basically, we should look into extension basically night to night, or even change, or does it change to night?
If I can mention another fun fact, in looking at the extinction curve on Mauna Kea, we realized there's a wavelength around 8,800 that's within 1% of being in space. We found this had been measured in the 70s from Mauna Kea, and we reproduced it. The extinction is 0.0. But no, the aerosol's so low. You just have Rayleigh, and Rayleigh's going down as lambda to the fourth. So before you get hit by water, right? It's you're 1% away from space.
How wide is that window?
It's not. It's really just being between water. So Rayleigh's going down, ozone's at about 1%. Well, I said it because right where it happens to occur, a lot of water starts coming in. Right, so it's between some water, but within one. And I think out in the near infrared, there are lots of bands like that are within 1% of space.
We do all our ground-based surveys in those windows?
Well, yeah, just deal with aerosol at that point.
Okay.
So I have a completely different question. So that you guys, for all of your, for your atmospheric modeling at VLT, you were focused on optical near IR. I'm a mid-IR astronomer, and ozone at 9.5 microns has always been my bane. Sophia made it even worse because it's like flying underneath like the ozone pockets at 500 miles an hour. I'm just curious if there's any way to tackle the ozone problem from the ground, because that's such a big hole in the in-band. And if this is completely off topic and you want to focus on other things, we can come back to it or not. So,
well, we have the ozone in here in something that actually I'm looking at. Also with people from Notice, an instrument on the future ELT, but it's also coming back to us because a future instrument on the VLT is cubes that will be looking the atmospheric cutoff, so between 300 and 400 nanometers, and we realize that we don't understand the ozone absorption
it's
enough.
So for people who haven't done ground-based mid-infrared spectroscopy, ozone basically takes you to zero transmission in multiple wavelengths between about 9 and 10 microns, 9 and 9.8, something like that. And so at low resolution, you're down to like 50% or 40% transmission. The problem is that I have never in my life been able to calibrate it out by like air mass matching or going back and forth. It's just, it's pretty variable. The ozone layer is way the hell up there. So monitoring precipitable water vapor helps you not at all.
No, but I can run ModFit on this. It's one of the things that we'd like to do.
So you're on it.
Yeah, when I find the time to do something about it, yes. But it's something, I mean, on the other hand, just to complete this, I mean, we
mentioned about the ozone thing, so I experienced ozone layers, but it's got the satellite data, so which correlates with the satellite data. So satellite can give us how much ozone was.
Okay.
That location, and then, interestingly, ozone layer changes in time. So.
Oh yeah.
So the French astronomer was keeping track of the brightness of the UV stars, and it keeps changing over the decades. So if you destroy ozone, we can get the UV light gets brighter, but you can see it. Yeah. And one more thing. So ground observation. Most of the observatory doesn't have the category of calibration. We are getting a hard time to get time for the calibration purpose. And if I write the proposal, it goes to stellar physics. And then stellar physics people don't understand what we are talking about. So we need a director level help.
Okay, so at ESO we accept the calibration proposal. So you're welcome to submit. And actually, Florian and I have been and Andreas Lofer, we have been very much working into this kind of category for proposals. But to come back to ozone, so with Florian and with Sabine Müller, we have been looking into this. We have put technical time requests to look into how much ozone is going to vary. There is a seasonal dependence. There is a dependence on the solar activity, and there is a day-to-day variation, but hopefully it should be relatively, we hope, we are going to check, we are stable during the night, just the 1 hour after sunset will be a bit uncertain.
Yeah, so just to give some background, I mean, we have talked to the scientists doing ozone. They also feel that the satellite data should be good enough for us. These, of course, are usually limb sounders that do this, so it's a bit of a different geometry. We probably will have a solar telescope, a very small one, on loan that will look at the total column and the aerosol optical depth, hopefully next year. And then we would have, let's say, half a year of measurements, and we would have a much better understanding daylight only, not the night. Daylight only, we would get some statistics, and as Alain said, we have some additional observations where we are particularly looking at twilight, what happens there, and then looking at the night at different air masses to get a better handle on this. But I mean, it's a lot of work.
So this is just kind of on topic. This has been a great meeting, but based on the talks that we heard today, I'd like to kind of gauge the interest in the room about whether it will be timely in the first half of calendar 25 to have a very focused workshop on understanding the angular and temporal correlations of the variable components of atmospheric transmission, which is aerosols, ozone, and water vapor, right? And I think our friends at ESO are making headway in that regard. We have some data from the calibration telescope at Rubin that wasn't presented here that I think is really quite timely, and it will certainly help us devise the observing strategy for our atmospheric monitoring telescope for the Rubin survey, for which we're really interested in understanding how to optimize that scheduler. So I'd just like to know if we put something together along those lines. Space people don't have to come because you don't care about this. But it's actually particularly germane for the Landau project also, because sitting there in geosync, we're going to need to know the atmospheric extinction at those laser wavelengths exquisitely well to reap the benefits of that project. So it actually bears on the wavelengths that are chosen. That bears upon what Greg just said. So it feels to me like that's a really sort of ripe thing and that it's quite timely. So were to put a bunch of people together to put this in motion, how many people would be interested? Raise your hand. Okay.
You'd organize it.
Sure, actually, yeah. Okay, that's enough. Thank you.
George, sorry.
I just want to make a comment. It sounds like you got your first working group for your cost calibration consortium.
So I'm struck how you need to have an absolute calibration that goes into the infrared. For example, the type 1A supernovae people need that. There's only one effort to improve that, and it only goes to 2 microns. So that means left it up to me and Luca Casagrande to solve that problem. That's a pretty slender read. There is a way you could, I mean, you could do some with JWST and NIRCam for sure. Another thing you could do is in the L band, the 3 to 4 micron atmospheric window, there are narrow bands that have very little atmospheric extinction. And I'm picking up on the point that if you center on the same place on an array, always the same time, and if you're oversampling the image, all the better, you could probably make a custom imaging photometer that would take very accurate data in one of these narrow bands. And that might be a way to get some really accurate stellar results. If you focus on stars with accurate interferometric diameters, then you can do the inverse infrared flux method and actually get absolute calibrations that way for a fair number of stars. So that might be something to think about.
Yes, thanks.
George, if the TAC approves our JWST proposal this cycle, so that we can actually find enough Z5 supernova and get Lakers for them, then we'll help you out. So right now they're just one-offs, right? You see 1 point on the light curve.
Krista's paper has 5 Z5 supernovae found with JW.
They're not standard. You don't run into the 1% or sub% accuracy requirement until your sample gets much, much bigger.
Well, but wait a minute. My point is,
no, I'm not distracting from your point. I'm just saying right now we don't have enough.
Expand a little bit. If you are depending on a calibration that you have only out to 2 microns, you're going to use a stellar model to match it, and you sure as heck would like to have a good point beyond what you're counting on to make sure the model is right. And that's what I'm thinking about, that going out to the wavelength where you really want to be calibrated, but with nothing beyond it, leaves you with a pretty risky situation in terms of the star doing something funny.
Understood. That's why some of us are working experimental calibration, so we don't depend on the models at all.
So who would be interested in doing this? Silence.
We had already a show of hands, I think. Yeah. That's, we have the specific,
Yeah. Maybe we can decide that during the workshop next year.
So another general comment is we have a lot of heritage photometry from various missions, and at some point we're going to have to try and really tie it explicitly into, what we're doing now, as it were, whether it's, IRAS, photometry and spectroscopy, or any of old catalogs, whatever, and that's a whole different thing, but also it bridges space to ground, because we have Gaia and we has observed everything, and there's a bunch of photometry from the ground for all those stars, and at some point we're going to have to figure out whether those are consistent or how to deal. And there's all this talk about the prism spectroscopy from Gaia. We also have to make sure that there's no systematics in that, all this kind of stuff. So there's a lot of work to be done, and unfortunately, I'm not allowed to do all that stuff. I have an instrument to support, but at least I can say someone should do it, which, of course, is easy to say.
Maybe a very specific point, and the tool, I think, by Richard, that, even on STIS, I find that you need to increase your box size from 11 to 21 pixels. I mean, this always brings me to the subject. Okay, how do we make sure that we can actually make the proper measurement on the science target? I mean, if we have a very good calibration, but we are not able to get the signals correctly on the science target, I mean, what is the point, right? So we need to be able to make the measurement itself correctly. And I mean, here we have a nice illustration, but I mean, if we are in a crowded field, we have a supernova on the galaxy, how do we make sure that we get the light properly measured to the kind of accuracy that we can expect?
So I do a lot of work at NIST with the Earth observing satellite community, and I'm just curious to what degree people like for this problem have looked at CRIS, EASI, or AIRS data, which is satellites flying all the time in low Earth orbit looking down. They're pretty big pixels sometimes. I'm not sure it's applicable. To what degree is this kind of data applicable, or have people tried to use this for atmospheric correction?
So I think that things that are on the upper part of the atmosphere, I think they're probably reliable. If you're trying to find things that are close to the ground, it's not. I mean, we've tried with water vapor. It just doesn't work. We have too much. I mean, we're on the summit of a mountain. Just too much changes from even a few kilometers.
They're like kilometer pixels and stuff. So.
So I guess since we're in a room with space and ground based, I want to turn around. Is there anything that we should, those of us who do more space than ground, that we could do that would help out with these issues of dealing with the atmosphere? What's the wish list? Is there one?
I mean, we could certainly think of some parallel observations, right? You have a few observatories like Landolt. That would be your artificial source, but we could also look at some natural sources, right? I mean, you observe from orbit, from L, whatever, and other people observe from the ground. And of course, you have to do a lot of characterization of the atmosphere on the ground to get even, so to say. But I think that would be a very interesting experiment to do. I mean, of course, it's complex logistically. Somebody has to approve it in multiple facilities, but I would argue it can be done.
But as long as it's a non-variable source, we don't have to do it at the same time.
Well, the point is that the atmosphere is variable enough. So if you try to do this, let's say, for 48 hours across the globe, then you will get all kinds of atmospheric conditions, right?
Space-based part.
The space-based part
shouldn't vary, right?
That one would hope, yes.
So having sources that we know the answer, and then do the ground from different places. Okay.
And I mean, things like your continuous viewing zones, right? Euclid or whoever. I mean, of course, that's no big deal. I mean, you just look whenever you have the opportunity.
We have some of those already, the CalSpec database, so there is already some.
Yeah, and the other thing, right, so we would have gotten as far as we did without CalSpec. Like, we don't know what's really going on where there's water absorption. We could say, does it look smooth? But then you look where water bands overlap the passion bands. You can't tell if it's right unless you have the space observations to see that we can then move from there. So there might be more targets that will help. Yeah.
How many targets do you need?
I think I know people to talk to, but it's
a useful thing to know.
Yeah. But some people have been working on that kind of thing, extending the white dwarfs and.
Yeah. But
yeah.
How much is enough?
Are we there yet? I don't know.
That's not a quantitative answer to that.
No, I'm saying I'm not the one who knows that. Are we there yet in terms of space observations? And I can only address basically the optical.
Yeah, right.
When you're thinking about this, are you thinking about telling people what the right answer is, or forcing them to try and guess the right answer and then checking it?
Oh, we're going to have the mystery.
Right, because when you start doing data challenges,
think we ought to have a lottery.
I mean, we could maybe do that. It'd be a little hard to hide the space data. We're not.
Right, that's the problem is you can't, right, but you would have to kind of tell people, you have like, right, or just, people aren't allowed to look at the answer or something. I don't know.
Fair enough, yes. I like the mystery part. That'd be fun.
Just another thought on that. I think you mentioned that you will have some radio sound launches in the preparation as well, right? We will have radio sound launches. So these campaigns where you would get the maximum characterization of the atmosphere. I think that would be the ideal opportunity to then make parallel space observations.
Okay. Oh, you've ended 3 minutes.
I think we could, people are if people are out of steam, I think we could stop here. It's all a great start, and I think that's what we want to do. So what's the deal, 6 o'clock?
Yeah, so at 6 o'clock, the reception will start in the cafeteria. They are setting up everything, the open bar, alcoholic, non-alcoholic drinks, and the food. So please come. You in about 1 hour. You can stay here if you want, go for a walk, go back to your hotel, come back here. If you want to use the shuttle, I think the last shuttle leaves from here at 6:30. Otherwise, you will have to walk or get another.
I'm going to show you this.
Huh?